Hi, I'm Hugh Breslin with Microchip's FPGA business unit. In this video, we're going to have a look at using the PolarFire SoC Bare Metal Library. We'll have a look at how to download the Bare Metal Library and the contents of it. Then we'll have a look at how to import projects from the Bare Metal Library, the default project build configuration, and the default debug configurations available for the projects. You've several options when it comes to downloading a copy of the Bare Metal Library. The repository is available on the PolarFire SoC Github page, and the Bare Metal Library is a pinned repository. When you open up the repository, you have a few options for downloading. If you click Code, you can select Download Zip, which downloads a zipped copy of the Bare Metal Library to your PC, which is probably the fastest way to download. Another option you have is cloning using GitHub Desktop. If you select this option, you're given a link to download GitHub Desktop if you don't have it installed, and if it's installed, it launches for you. The URL is pre-populated for you for the repository, and then you simply set the local path where you'd like to clone the repository into, and click the clone icon to actually download a copy. Now that the clone's finished, you can browse the files of the repository, and also you'll be notified if there are any changes to files in the repository, so you can see if there are updates to the Bare Metal Library. If we have a look at what's actually in the Bare Metal Library, if I open it with Explorer now, you've downloaded two folders, one's called Source and the other one is called Examples. The Source folder contains a platform folder, and this follows the folder structure of a bare metal project targeting PolarFire SoC. The platform folder contains a copy of the HAL and the Mpfs HAL, which are used running the bare metal application, and it also contains a drivers folder with a copy of all of the PolarFire SoC MSS peripheral drivers, and finally contains a config folder for the system configuration. This can be dropped into an existing project if, for example, there was an update to the Mpfs HAL or the HAL, or if a new driver came out, the updated platform folder can simply be added in to update the drivers. The other folder that gets downloaded is the Examples folder. The Examples folder has a project folder for each of the MSS peripherals. So for example, if I select MSS MMUART, I have an Mpfs MMUART interrupt example project that I can import into SoC console, and this will demonstrate the use of the UART drivers. And for example, again I could go into the MSS RTC, and in this case there are two example projects available. So different drivers will have different projects available to demonstrate how to use them properly. The easiest way to import a bare metal example project from the Bare Metal Library into SoC console is by selecting File, Import, and then in the General tab of the Import window, select Existing Projects into Workspace. And then browse to the location where you downloaded the Bare Metal Library and select the folder. If you can't see any projects listed, make sure the Search for Nested Projects option is selected to search for any projects in subfolders. Then you can select a project to import. As there's quite a few projects in the Bare Metal Library, you can probably deselect all of them and then only import the project you'd like. So for example, if I wanted to import the Mpfs MMUART interrupt example project, select it from the right and then click Finish. SoC console imports the project, and then it'll show up in your project workspace on the left hand side. Another way to import projects is directly using the SoC console Git plugins. To do this, in GitHub, select the code icon of the repository you want to clone, and then copy the HTTPS URL that can be used with another Git or SVN client. In SoC console, select File, Import, and then under the Git heading, select Projects from Git with Smart Import. When you click Next, select Clone URL, and then the field for URL, host, and repository path are automatically populated from the link that was copied from GitHub. You can select Next, and then SoC console will discover the branches for the repository, and the Bare Metal library only has a master branch available now. I'll click Next, and then you select the directory you would like to clone the Bare Metal library into. So I'd previously cloned the Bare Metal library, so I'll create a new folder now called PolarFire Bare Metal Library 2. And when I select that folder, I can click Next, and SoC console will clone the Bare Metal library and then display the available projects to me. Now that the clone's complete, I can see all of the available projects to import listed off here. And the MMUart interrupt project is already grayed out as I've imported it into my workspace. So for example, again I'm going to deselect all of the projects, and in this case I'm going to select the RTC interrupt project to clone into my workspace, and I can just click Finish to import this project. And I can see it's popped up now in the Project Explorer on the left hand side. Now that I've cloned a copy of the Bare Metal repository or the Bare Metal library into SoC console, I can import more projects as I want. If you select View and then Show View and then Other, there's a Git option to choose from, and in here select Git repositories and then click Open. As I've cloned the Bare Metal library, I can see it listed as a Git repository, and if I go into the working tree, I can see my source and examples folder listed off. If I right click on the examples folder, I can select Import Projects, and then SoC console will once again give me a list of available projects that I can import into my workspace. Now let's have a look at the default build configuration for any of the projects downloaded from the Bare Metal library. I've already imported the Mpfs MMUart example project, and if I right click and select Properties, the project properties open up for me. The build settings can be found in the C/C++ build tab in the settings heading, and under here you can see the target processor settings, the optimization settings, and so on, along with any build steps in the project. And let's start looking there. So in build steps, there's a command added in as a pre-build step. So this will run before the build actually occurs. And it's running the SoC console built-in Python binary, and it's going to run the Mpfs configuration generator. This script is actually included in the Bare Metal library projects, and it's available standalone as a repository in the PolarFire SoC GitHub organization. The script actually gets run on an XML file that's contained in the source folder, in boards, and then in an iciclekit-es folder, and an SoC FPGA design folder, and then in an XML folder. And it's going to export the XML configuration into the source, boards, iciclekit-es folder. So if we have a look at that now, in the source folder we have a boards folder, and in here we have the iciclekit-es folder. We've got an SoC config folder and an SoC FPGA design folder. The SoC FPGA design folder contains the XML that gets generated from a Libre project, and this contains the eMMC default configuration that comes with the iciclekit, and the XML can be found in the reference design repository on GitHub. The SoC config folder contains the header files that are generated from this XML file using the design or the XML generation script. So when the script is run, this folder here is updated with the latest SoC configuration. So that's the first thing to look at in the build configurations. And if I open them back up, so that explains the Python script that gets run. And if you update your design with a new MSS configuration with updated XML, you can drop it into this folder here to automatically regenerate your project header files. Then in the Tool Settings tab, there are several options. So for target processor, the main one that's selected is the architecture. So this is set to build for an RV64G with a compressed extension enabled. The integer ABI is set to LP64 from the available options. The floating point ABI is set to double precision or D. The tuning is set to the tool change default, and the code model is set to medium NE. Small data limit is set to 8, and align is set to strict. Optimization is disabled for any of the included example projects, and none of the warnings are enabled. And the debug level is set to maximum. In the Cross-C assembler, there are some there are no preprocessor defines included, and there are several includes. So the first is to include the source application directory, which you can see over on the left, which contains the folders that contain the C files for the E51 and U54 cores. We include the platform folder, which contains our Mpfs HAL, for example, and our linker script. We include the platform config reference folder with a reference SoC config design. And we include the source boards Icicle Kit ES folder with our SoC config in it. There are no warning flags enabled, and there are no miscellaneous options enabled as well. In the Cross-C compiler, again there are no preprocessor options, and the same includes are given as per the assembler includes. And the optimization standard is set to GNU ISO C11 with no optimization flags. There are two warnings for warn if a function has no archetype and warn if wrong cast. And the only miscellaneous option is generate assembler listing. The GNU Cross-C linker heading allows you to pick the linker script, and the default linker script uses the Mpfs lim. There are a few example linker scripts that you can choose from. If you double click on the linker script and then select workspace, you can browse for a linker script in your workspace. So if I go into the source, platform, and then platform config reference folder, I can find a copy of the included linker scripts. So the Mpfs lim is the default linker script used. There's also a linker script for the Mpfs lim along with an LMA scratchpad VMA. We can target the envm. We can also target the dtim and the DDR using the E51. There are no libraries listed for the linker script, and there are only two miscellaneous options selected, which is use newlib_nano and do not use syscalls. For create flash image, an Intel hex image is created from the available options, and in Cross-C, create Cross-C listing, there are several default options selected, and the default or the RISC-V cross print size is set to sysv from the available options. And those are the default configuration settings for a soft console build of a project from the Bare Metal Library. Now let's have a look at the default debug configurations for a project that's downloaded from the Bare Metal Library. I've already got a copy of the Mpfs MMUArt interrupt example project downloaded and open. So if I open up the debug configurations now, I can see there are 3 included configurations. The first is an Mpfs MMUART interrupt hardware all hearts debug configuration. This is a debug configuration for running on target hardware, such as an icicle kit. It's going to load my C application from my build configuration name, so whether I built in debug or release mode, from the Mpfs MMUART interrupt project. And it's going to load an elf file called mpfs-mm-uart interrupt.elf, which matches the name of the example project. In the debug tab, OpenOCD is started, as we're debugging on a hardware target. It has 2 default commands. The first is --command set device Mpfs, which says that we're targeting an Mpfs device. The second is --file board microsemi-risc5 config to load the microsemi risc5 OpenOCD configuration. Then GDB is started, and it has 3 default commands. The first is set $target_risc5 equals 1 to say this is a risc5 target. Then we set mem inaccessible by default off. And then finally, the last command is to load our elf, which is file $config_name mpfs MMUART interrupt and then mpfs MMUART interrupt.elf, similar to the elf loading in the main tab. In the Startup tab, initial reset is selected to reset our target when we connect. We load symbols from the project binary, which is mpfs MMUART.elf. We also load the executable from the project binary. And then finally, in the run/restart command section, the command thread apply all set $PC equals _start is executed. And then at the very end, we set a breakpoint at the E51 main function, and we also set the continue option to execute from the reset vector to this breakpoint that we set at E51. Another debug configuration that's included is the Mpfs MMUART interrupt renode all hearts debug. So this is a debug configuration targeting the Renode emulation platform. It has the exact same main, where we pull the elf file from our current configuration, and in the debugger tab, the only difference is that OpenOCD is not started, as we're not targeting a hardware target. GDB is started though, so it can connect to the Renode GDB server. And in the Startup tab, the initial reset is also selected, and some monitor commands have been added in to show the UART analyzers for the UARTs that are available in the system. ARM semi-hosting is enabled in this configuration, and then we load the symbols and the executable from the project binary again. And then at the end, the thread apply all set PC equals _start is also applied, and then monitor start command is run to start the emulation in the Renode system. And then again, a breakpoint is set at the E51 main, and the continue option is selected. And the final thing that's included in the debug configurations is a launch group. So there's a launch group called Mpfs MMUART interrupt renode all hearts start platform and debug. And what this does is it starts the Renode external tool for the icicle kit, and then launches the OpenOCD debug configuration that's shown over here on the left hand side. So instead of having to start Renode and then start the debug configuration, you can use the launch group to do both tasks in one thing.